Let us look at limits and continuity of some trigonometric functions. So, I will start by showing that the trigonometric functions sine and cosine are continuous. The first step is to show that the sine function is continuous at x equals 0. Now, before we do this, let us quickly recall the definition of sine. Sine is defined geometrically, as you know. So, if you have a circle of radius 1 centered at the origin, the horizontal line is the x axis, then take an angle of x from the horizontal, then drop a perpendicular from the point where this ray meets the circle down to the x axis. Now, if you look at this right angle triangle, then sin x is the ratio of the opposite side to the hypotenuse of this angle x. The hypotenuse is, since it is a unit circle, this hypotenuse has length 1, and so this vertical has length sin x. If we are considering an angle x that is negative, then this will lie just below the x axis and sin x may be negative, but in any case this vertical line will always have length absolute value of sin x. The angle x is going to be measured in radians, so that the full circle has angle 2 pi. Now, I claim that the absolute value of sin x is in fact less than the absolute value of x. Why is that? Now, we can do this, see this quite nicely geometrically by considering this triangle. So, this shaded triangle here, what is its area? So, remember the area of a triangle is half base into height. The base of this triangle is a radius of the unit circle, and so this distance here is 1. The height of this triangle is sin x. So, the area of the triangle is half into the absolute value of sin x. Now, let us also consider this slice of this pizza here, the circular sector, which I am shading in a different color, which is certainly larger than the triangle, right. So, what is the area of this sector here? The area of this sector is x divided by 2 pi times the area of the whole circle, pi r squared, but r here is 1. Now, this sector here is clearly contains the triangle, and so the area of the sector is greater than or equal to the area of the triangle. Now, if we want to also think about the possibility that x might be a negative angle, then I should put an absolute value of x here. As long as we are in the first quadrant or the fourth quadrant, this will be fine, we can put absolute values. And so, what we have is that half absolute value of sin x is less than half absolute value of x over 2 pi into pi, and just cancelling out we get absolute value of sin x is less than or equal to absolute value of x. So, given any epsilon greater than 0, take delta equal to epsilon. So, if absolute value of x minus 0 is less than delta, which means that absolute value of x is less than epsilon, which implies that absolute value of sin x is less than epsilon, and this proves that the limit as x goes to 0 of sin x is equal to 0. This proves that the limit as x goes to 0 of sin x is equal to 0. Now, remember sine of 0 is 0, and so in particular what we have shown is that the sine function is continuous at 0. We will now come to the second statement, which is that the sine function is continuous at every real number. So, I will say that sin x is continuous on R, which means that sin x is continuous at A for every A in R. In order to do this, we would like to bound the difference between sin x and sin A. Now, from trigonometry, you might recall that sin x minus sin A is 2 cos x plus A by 2 into sin x minus A by 2. Since sine and cosine always take values between plus 1 and minus 1, this cos x plus A by 2 lies between plus 1 and minus 1. So, this is always less than or equal to 2 times absolute value of sine x minus A by 2. But by what we just did earlier, this is less than or equal to 2 times absolute value of x minus A by 2, which is equal to the absolute value of x minus A. So, what we have shown is that sin x minus sin A in absolute value is less than or equal to the absolute value of x minus A, at least when x is close to A. So, given any epsilon greater than 0, take delta is equal to epsilon, and what we have is if x minus A is less than delta, then clearly sin x minus sin A is less than epsilon. Similarly, it is easy to show that the cosine function is continuous on R. We use a very similar formula, which is that cosine x minus cosine A is equal to absolute value of, well, so cosine x minus cosine A is minus 2 sine of x minus A by 2 times sine of x plus A by 2. And this is less than or equal to 2 times, well, the sine function takes values between plus 1 and minus 1. So, I can just write this as sine of x minus A by 2, which is less than or equal to absolute value of x minus A. And so, once again, for every epsilon you can take delta equals epsilon and prove the continuity of the cosine function at any point A in R. Now, the third result that I will prove in this lecture is a very interesting limit. The limit as x approaches 0 of sin x over x is equal to 1. For this, we go back to the diagram that we had. We will prove it geometrically. So, remember that if you draw this vertical line, then its height is absolute value of sin x. We also completed this triangle over here, and now for this I want to just extend this line from 0 to meet up with a vertical line drawn from the x axis. We have a larger right angle triangle and its base is of length 1. The angle here is x. So, the height of this line here is tan x. And just to be safe, if I am looking at x less than 0, I need to put absolute value of tan x. So, now I have 3 regions. Firstly, I have the smaller triangle that we had considered earlier, which I am shading in blue. We have the circular sector, which I will shade in red. And finally, we have this larger triangle, which I will shade in green. Comparing these 3 areas, what do we have? The smallest triangle has area half into absolute value of sin x, the circular sector has area absolute value of x by 2, and finally, the larger triangle shaded green has area half into absolute value of tan x. So, we have inequalities like this. Now, we can divide throughout by sin x and multiply throughout by 2. What we get is absolute value of, so if we divide throughout by absolute value of sin x, first quantity just becomes 1 is less than or equal to absolute value of x over absolute value of sin x, and that is less than or equal to tan x is sin x by cos x. So, I get here 1 over absolute value of cos x. But this is the same as flipping over the fractions and reversing the directions of the identities. So, what I get is 1 is greater than or equal to absolute value of sin x by x is greater than or equal to absolute value of cos x. Now, if x were positive, we would not need these absolute values. What happens if x is negative? Well, if x is negative, sin x is negative, and well, x itself is negative. So, once again these absolute values are not needed. So, we can remove the absolute values here, and we are anyway looking at x close to 0, in which case cos x is also positive. So, we can remove these absolute values here as well. Now, note that since cos x is a continuous function at x equals 0, we have limit as x goes to 0 of cos x is equal to cos 0, which is equal to 1, and here limit of the constant function 1 is also 1. And so, what we have is that this, by the squeeze theorem, the limit of sin x by x as x goes to 0 exists and is equal to 1. And so, we have proved that limit as x approaches 0 of sin x by x is equal to 1.